For our project, we developed quantum Merkle trees. Arya Graeli.
I'm John Dunbar. So, quantum Merkle trees are a new interesting development in the field of quantum computing, and of March this year, a paper found them to be theoretically possible. So, what is a classical Merkle tree? First of all, so a classical Merkle tree is like a fully filled out tree with two children at each node, and there's data at the bottom. And at each intermediate step, we take the combined hash of both the children. So, why is that useful? If we had a prover which had this database, and we want to get the value of something like L2, but we don't trust the prover, this problem comes a lot like in distributed systems. There may be a source of truth, but maybe it's like too busy and it can't fulfill requests for random data like what is L2. But thanks to the Merkle tree, it only has to tell us the value of the top hash. And in practice, there can be decentralized systems for agreeing on this top hash. So we know the top hash now, and our untrustworthy prover gives us this subsection of the tree. We can easily validate the prover's work and prove that L2 has not been tampered with. Notice the prover only needs to send a small portion of the entire database to us. For instance, if we were communicating over the internet, it would take way too long to send an entire database. And we can trust the value of L2 because if the prover wanted to trick us into a fake value of L2, it would take an impractical amount of computing power to fake all these hashes. Now, this is extremely useful in cryptography. It has uses in like preventing file system corruption, to the Git version control system, to decentralized cryptocurrency. So, how is quantum different, though? First of all, some terminology. In cryptography, we like to use what's called a random oracle, which is kind of like a theoretical ideal hash system. It converts any number to a truly random other number in a deterministic way. Unlike regular bits, quantum bits exist on a continuum. They could be 1 or 0 with 100% probability, or in like a superposition with partial probability of being either 1 or 0. And we can make a quantum random oracle that is analogous to our classical hashing algorithms on this. However, fundamentally, qubits are not this one-dimensional. They exist in quantum states, or in complex states with two dimensions, real and complex. So an evil prover could flip the phases of the data qubits, and our quantum oracle would not be able to tell the difference, and thus fool our verifier. And we want a quantum solution to this because our universe is fundamentally quantum. As we improve our understanding of physics, we find more and more ways that the world is quantum mechanical, and we're finding ways that this quantum mechanics can improve our lives. For instance, using quantum tunneling, we can make extremely small and simple transistors, like in this picture. However, quantum states are computationally expensive to represent using classical ones and zeros. Thus, it's very useful to have sufficiently advanced quantum computational techniques to deal with these quantum states. And the quantum Merkle tree also has useful insight into the gap K local Hamiltonian problem, which is a currently unsolved problem in computational complexity theory. So we want some deterministic way to take the data of a tree node, two children, and convert it into a sufficiently randomized quantum state. Although a previous random oracle was random in the classical sense, it was not random for quantum states. So we need a model which can approximate that, which is called the quantum Haar random oracle. And it outputs states which are evenly distributed among all the quantum states. So using a Haar random oracle model, we created the first concrete implementation of a quantum Merkle tree.
All right, now we'll head over to the notebook itself to go over its implementation. So again, this is our implementation of quantum Merkle trees. We did reference a paper that proposed, the math behind it and proved that this is possible. And we were at least first, there was no open source implementation done before, so we implemented this ourselves. As you can see, this is implemented on IBM Quantum Lab. And our initial step is just import the associated libraries with NumPy, Qiskit, and load our IBM Quantum account. And then we will move on to the quantum utility functions that we use throughout our model. So we first have a QR-Har method, which is going to generate the quantum Haar random oracle model matrix. So this matrix will be representing our unitary gate when we apply it in our circuit. And this is just generating a matrix of size n that can apply that Haar random oracle. Then we move on to pool qubits, which is just a useful post-processing method that we remove separately because once you run a result in the back end, you'll get a set of state vectors and counting which ones are most apparent, and then converting those into the qubits themselves by getting whichever ones was the most likely to be there is just what pool qubits does, and it's useful for converting a one state of then applying the model to it and then getting the next quantum state. So onto the prover and verifier itself. As we mentioned, the prover is a person who has access and control over the entire database. So your classical Merkle tree has the merge hashes then that are being constructed towards the root. Whereas on the other hand, the verifier is the person who's communicating with the prover to make sure that the data hasn't changed in any way. In a classical sense, hash functions are still valid, and our interpretation will be the qubits are still valid, and then also can be used to query to see what is the value stored in the database at this position. So onto the prover itself, the main function is the build Merkle tree method right here. It'll take in an input which we call sigma. Sigma is just L sequences of B qubits, and it initializes the tree. If you think of a tree as flattening it into a 2D array, if it has L leaves, it'll have 2 times L amounts of nodes in the trees. And what we do is we initialize all these leaves and then bring it all together by merging the children together using the Har oracle method, which I'll get into right now. So this Har oracle method, all it does is it'll apply the Har random oracle model onto the inputted qubits. So it'll first take a quantum register, and send that into our quantum circuit, apply then the unitary gate that's representing the Har model, that's the Har matrix that we pre-computed for size n. And then we also have to add some classical registers because at the end of the day, what we do is we measure the states of the qubits. As you can see right here in circuit.measure from the quantum qubits, or from the qubits to the classical bits. And then we run in our backend, pull the result, get the counts, pull the results, and get a new set of qubits that are representing the new values in that node. And then on the verifier side, the main method here is get block I, where given an input, it's going to check if the database has been tampered with, and if not, then it'll return the value that's stored there. So quick overview of how it works. Really, the key is that it's just unwinding the actions done by the prover, but with Har oracle, where it's running the inverse, as you can see, the inverse of the unitary gate to basically decrypt those qubits back into its original state. And again, the classical registers and measuring and all of that is still being applied. So with all that, basically our Merkle tree is done. And we wanted to test, to see if this works. So we had an input with just, four sequences of 2 qubits. And we had it as 4 just to, be a power of 2, so the tree is perfectly balanced, but this could be any value. You'll just add dummy qubits to, make it a balanced tree. And we initialize our prover, our verifier, build the Merkle tree. And then from here, we do some tests to make sure that, when it's querying the value, can it get the right value? And then also, if it queries a different value, making sure that, your database is still working properly, you're extracting the right values. And then this is the main test to see if the prover and verifier are interacting correctly, where we change a value in the prover, and we see that the verifier will pick up that this database has been changed, and I can no longer trust the prover's outputs. So this is another instance of it, which is changing the entire tree itself. But this is pretty clear that it's showing that the Merkle tree is working, and this isn't a classical Merkle tree, rather this quantum Merkle tree is working with this set of inputs. And feel free to download this notebook, mess around with the values. You can use bigger inputs, but they'll take longer. But yeah, thanks for listening. And we hope you enjoyed it.